So hello again everybody, and welcome to the Cryosphere Pavilion for this event that's going to be looking at emerging evidence of abrupt changes in the Antarctic environment. So my name's Chris Auckland. I'm one of the early career scientists with the ICCI and based at the University of East Anglia. And today we're going to be hearing from the Australian Antarctic Division, and they're going to be talking about the emerging evidence of abrupt changes in the Antarctic environment. So take it away, guys.
Thank you very much for the introduction, and thank you for people who've been able to join us in the room and online today. So this is work that that's developed out of the Australian Antarctic program, looking at the evidence that we're seeing for abrupt changes in the Antarctic environment. So this is work. Sorry, I'll just get there we go. The slide to progress. So in the Australian Antarctic program, we have a number of major scientific programs. And so this is work that we coordinated across all of those major Antarctic programs. So I'm Nerily Abram. I was the lead author on this work. I did the work as part of the Australian Centre for Excellence in Antarctic Science, and I've since moved across to become the Chief Scientist at the Australian Antarctic Division. We also have contributors to this work from Securing Antarctica's Environmental Future, the Australian Antarctic Program Partnership, and the Australian Antarctic Division. And I'm really pleased that some of the co-authors have been able to join online today as well. And so we'll work as a team to present the different sections of the work to you. So these are the people who will be online today. So there's myself, Nerily Abram. We have Ariane Purich from Monash University, Matthew England from the University of New South Wales, Jan Strugnell from James Cook University, and Barbara Weinecker from the Australian Antarctic Division. So to set the scene for this work, and this probably is a graph that's very familiar to everybody in the room, showing how human influence has warmed the atmosphere and that unequivocal human connection to the warming that we're seeing across the atmosphere, the ocean and the land. And as a response to human-caused global warming, many of the changes that we see in the climate system scale directly to how much warming we have. And we can see this as an example here, showing expected rainfall changes at different levels of global warming. And the thing to take away from these images is that the patterns that you see are very similar across the different global warming levels. But as the warming intensifies, so do the impacts. And so this leads to this this notion that every fraction of a degree of global warming matters in terms of the impacts that we will face because of human-caused climate change. And while many of the changes that we expect in a warming world will scale and become worse with every fraction of a degree of additional warming, not all changes that we expect in a warming climate will happen in that way. And that leads us to this concept of abrupt change. And this is where a system can change substantially faster than what we would typically expect to be the way that system would change. These can be seen in changes that are known as regime shifts, and this is where a system changes and we can see statistically that it has moved from one state to a distinctly different state. And we'll talk about some regime changes that we're seeing in the Antarctic environment in the talk today. Another aspect of abrupt change can be tipping points, and tipping points are where a large-scale part of the Earth system changes abruptly and sometimes irreversibly when a critical threshold of warming is breached. There are many tipping point elements that are known to exist in the Earth system. This is one map showing a schematic of where we expect there to be tipping points in the Earth system. And one of the things that we see in a map like this is that the majority of these known tipping elements sit in the Northern Hemisphere. And that doesn't mean that we don't expect there to be similar processes that can happen in the southern hemisphere. What it means is that we haven't had the scientific evidence to be able to really understand what the tipping point risks are and the abrupt change risks are in the Antarctic and Southern Ocean. And so that's been the state of play for a number of years, a number of decades, up until recent years. And so the genesis of the work that we're talking about today came about around 2023, when we just started to see a whole host of really dramatic and worrying changes developing across Antarctica and the Southern Ocean. And we'll touch on the scientific evidence that we're seeing around these in the talk today. So the talk today is based on this paper that was published in Nature a couple of months ago, looking at the emerging evidence of abrupt changes in the Antarctic environment, looking across changes that we're seeing in sea ice, ocean circulation, the ice sheets, and the biological systems and how they all interact. We've also produced a policy briefing to move from that scientific paper into a plain language summary that we hope is useful for decision makers in thinking about how we actually address the risks of abrupt changes coming from the Antarctic environment. Hopefully on your screen you can see a QR code. I'll show that again at the end. That will take you to a page that links to both an accessible version of the scientific paper, but also the policy briefing document. I just wanted to touch on this concept of what we mean when we're talking about abrupt changes today. And abrupt has different meanings depending on what part of the system we're talking about. So we're talking about changes that, if we're thinking about an ice shelf, an abrupt change can happen on the timescale of days for an abrupt ice shelf collapse. When we're talking about changes in sea ice, they might unfold over months to years. But when we're talking about the loss of ice from the ice sheets, those are changes that will take place over decades to centuries or even longer. But the key thing to remember from the policy side is that even when we're talking about abrupt changes that will play out over decades to centuries, it's the choices that we're making in the coming years to decades that are going to set those in motion. And also just to mention, I showed there the policy briefing that we developed for an Australian audience of policymakers when the paper came out. We're currently just finalising an international version of this that will be published through the Antarctic Environments portal, so that will be available in the coming weeks as well. Right, I'd like to now pass over to Ariane to talk about sea ice.
Thanks, Narali. So sea ice seems like a good place to start when we're going through the different abrupt changes that we're seeing around Antarctica, because we've seen some very, very dramatic changes in Antarctic sea ice over the past recent years. But let's take a step back and think about what even is sea ice. So sea ice is the frozen ocean that's occurring around Antarctica, and it really waxes and wanes with the seasons. And it's important in the Earth system for a number of different reasons. So firstly, sea ice is white. This means it reflects sunlight back to space and it helps keep Earth cool. When sea ice forms, lots of the salt from the ocean water isn't incorporated into the ice, and this very salty brine is rejected from the sea ice and it drives global ocean circulation. And sea ice also provides habitat for southern ocean species like penguins and krill, and so it's really important in ecosystems. So we really care about what is happening to Antarctic sea ice. Next slide, please. So looking at a time series of Antarctic sea ice, so this is showing deviations in sea ice compared to normal over the satellite record. We can see that for decades, Antarctic sea ice stayed pretty close to normal. You can see the sea ice is just wiggling around the zero line. And then you can see from about 2010 to 2014, we actually had more sea ice than we'd expect. But what we've been really concerned about over the past decade is when we look at 2014 down to 2016, we saw this massive decline in Antarctic sea ice. So in the space of 2 years, the Antarctic lost as much sea ice as the Arctic lost in 3.5 decades. This is a really abrupt change in sea ice. And you can see that since 2016, Antarctic sea ice has stayed mostly far below zero. So we have been seeing repeat record minimums in summer sea ice extent since 2016, and then since 2023 we're seeing very, very low record winter sea ice extent. Next slide, please. So this looks like the map shown on the left. And so this is showing the sea ice extent around Antarctica in July 2023. So we can see the map of Antarctica in the middle and the areas of white around the edge, which were areas that were covered in sea ice in July 2023. But the areas that were usually covered in sea ice are encompassed by the grey line. And you can see all the areas shaded in orange or missing around Antarctica. Now, you might think these are just some areas around the edge, but the scale of how much of the Southern Ocean is covered by sea ice is just so enormous that these orange areas add up to 2.47 million square kilometres. This is almost the size of Argentina of sea ice that was missing in July 2023. And this is going to have huge impacts to the climate system, to ecosystems, to the ocean functioning. And so this change was so abrupt, it was so unexpected, scientists have been really concerned in understanding it better. This change represented a 7 standard deviation drop in the sea ice coverage around Antarctica. Now, at this point, statistics don't really mean very much. 7 standard deviations is so enormously low that it's totally crazy. And so this led many people to say, well, are the statistics really meaningful? Is our observational record long enough to think about these drops in sea ice outside what we'd expect? So we need a longer time series of sea ice. We need to be able to consider how unusual was this drop in sea ice in July 2023 and really this decline in sea ice since 2016. Next slide, please. And so is the observational record, yeah, here we go, thank you, Neroli. And so when we turn to reconstructions, we can look at longer records of Antarctic sea ice. And so the satellites go back to 1979, but we can estimate how much sea ice there was using relationships between sea ice and historical observations of things like pressure and temperature. And to do this, we can reconstruct Antarctic sea ice over the 20th century. And so in the orangey brown colour, we've got a reconstruction of Antarctic sea ice going back to the beginning of the 20th century. And in this figure, you can see that for the most part of the 20th century, sea ice has this weak declining trend. But firstly, what we're thinking about is how unusual was the 2023 drop in sea ice. And so for context, behind the lines, the reconstruction lines and the satellite observation lines, we've got grey shading showing 3 sigma ranges, so 3 standard deviations. And you can see that across the 20th century, at no point did the reconstruction or the satellite observations exceed -3 standard deviations until winter in 2023, when sea ice dropped down to its really, really low, record low. And this historical context is providing us with confidence that what we're seeing now in Antarctic sea ice is very, very unusual on this century-long timescale. And these changes are happening very abruptly. Next slide, please. And so if we extrapolate the rate of decline in sea ice, we can further see this. So here we've got this arrow, which is showing the linear rate of decline over the reconstruction. And we can see that over the 20th century, sea ice around Antarctica is declining gradually. We can see we have this blip above normal around 2013, 2014, and then the drop in 2016, which still could be considered as a continuation of the 20th century sea ice decline. But what we're seeing is that since about 2023, the sea ice loss is far below this linear decline. We're seeing that sea ice is now declining in a non-linear fashion. This is indicating an abrupt change in Antarctic sea ice or a regime shift. Next slide, please. And so we're really interested in what are the consequences of this decline in sea ice and understanding it as an abrupt change or a regime shift. And for thinking about this and putting it in context, we want to compare changes around the Antarctic, which are happening recently, with changes in the Arctic, which have been studied for decades and which are well understood by the scientific community. And so the next slides that I'm going to go through are going to be comparing the Arctic and the Antarctic. Next slide, please. So to start with, we look at time series of the sea ice maximum. So this is the sea ice at the end of winter, which is in September for the Antarctic, and this is shown in purple, and this is in March for the Arctic, shown in blue. And we're seeing now that the recent rates of Antarctic sea ice decline over the past decade are rivaling the magnitude of the well-known Arctic sea ice loss over the past 45 years. So you can see we've had this steady decline in Arctic sea ice over the satellite period, but now the decline in Antarctic sea ice is occurring at a greater rate than what's seen in the Arctic. Next slide, please. When we look at the summer minimum sea ice, so this is sea ice coverage in the Arctic at the end of summer in September, and in the Antarctic at the end of summer in February, we can again see that the rate of change in the Antarctic is exceeding that in the Arctic. Now, this is particularly notable because the IPCC 6 assessment report states that the Arctic Ocean will likely be practically sea ice free, which means less than 1 million square kilometres of sea ice, in September at least once before 2050. If the current trends in Antarctic sea ice continue, then the Antarctic could experience sea ice-free summers sooner than the Arctic. This will have really important implications for the species that depend on sea ice to live. And so we're seeing that this very rapid, abrupt changes in sea ice are happening very, very fast around Antarctica and will have these flow-on consequences. Next slide, please. Now, one of the really important consequences of this low sea ice happens because sea ice is white and it reflects sunlight back to space and it helps keep Earth cool. And so I put this figure here because I really like to highlight again just how vast Antarctic sea ice coverage is. So we can think about springtime when the sea ice is still covering a really large part of the Southern Ocean. It's extending quite far north and it's reflecting lots of sunlight, helping keep the Southern Ocean cool. When the sea ice is missing, this sunlight is absorbed into the ocean and really warms the Earth. Next slide, please. And so we can calculate a measure of how much sea ice is helping to cool Earth, or when we compare it, how much it's effectively warming Earth because we've lost it. And this is important because we've known that the Arctic sea ice has been declining for decades, and this has been one of the reasons why the Arctic has been warming at a much faster rate, 3 to 4 times the global rate of temperature over the past 45 years. And so we know that Arctic amplification is happening and Arctic sea ice loss is contributing to this. When we consider how much radiative effect, how much possible warming could be occurring because sea ice is being lost around the Antarctic, we're seeing that the Antarctic is now catching up with the Arctic. And this could mean that as Antarctic sea ice is lost, we see an acceleration of warming around the southern hemisphere high latitudes. And this is really, really significant in a region that has to date not warmed as fast as the Arctic. Next slide, please. And so I'm just going to skip through these next slides in the interest of time, but we have further evidence from climate simulations that we are committed to these abrupt changes in Antarctic sea ice. So in climate simulations where we switch to net zero at different greenhouse gas concentrations, we can see that global temperature largely stabilizes, but not quite. So we see these different red and orange lines. They're showing different net zero scenarios with small temperature rise going forward. Next slide, please. When we look at the evolution of Arctic sea ice extent in these simulations, we see that Arctic sea ice coverage in winter and in summer, it stabilizes. When we cut emissions, the Arctic sea ice decline stops. And so this is showing us that Arctic sea ice is not a tipping element due to its linear response to warming and reversibility. Next slide, please. And so we can also view this, these plots on the right are showing the evolution of Arctic sea ice in global warming levels rather than in time. And what we're really looking at here is that the Arctic sea ice is declining linearly with temperature. So when we cut emissions, we stop the decline in Arctic sea ice. But I spent so much time telling you about this because, next slide please. The Antarctic looks very, very different. What we see is that even when we cut emissions to net zero, the Antarctic sea ice continues to decline. We see a decline in sea ice in winter, we just see a decline in sea ice in summer, and we really see this in the global warming levels. Sea ice continues declining. And this means that Antarctic sea ice has commitments for ongoing decline even after climate stabilisation. This will have far-reaching implications, and one of these is to the ocean. And so next I hand over to Matt.
Thanks, Ariane, and thank you everybody for giving us the opportunity to present today. I've been given 10 minutes to talk to you about the Antarctic overturning circulation. In the next slide, you'll see a lovely animation. It does take a few seconds to play. Just wait for that little cursor to move along. It's going to animate these arrows, but basically what you see here is the overturning circulation of the world's oceans. I know the North Atlantic, the cousin of the Antarctic overturning, is very well known to the community across into public fora. There's even been a Hollywood movie made about that overturning circulation. Unfortunately, the animation seems to have stopped, but anyway, you saw the arrows moving. That overturning circulation in the North Atlantic has an equivalent overturning off Antarctica, and those blue arrows you see there indicate the flow of water off the Antarctic shelf into the ocean's abyss. And this is such a significant overturning that the bottom 2 kilometers of the world's oceans, that's a massive slab of water, is almost entirely ventilated from this water originating around Antarctica. Next slide, please, Neroli, thank you. Just here is, now I'm showing you a different perspective. This is now latitude along the x-axis and depth in the y-axis. And you can see these blue bold arrows forming off the Antarctic continent. So that black bit of landmass there is the Antarctic shelf, showing this bottom water forming off Antarctica, sinking to the ocean abyss. It drags along the bottom of the seafloor. It stirs up nutrient-rich water there, and that nutrient-rich water recirculates back up to the surface where it feeds marine ecosystems. There's other important aspects for this overturning circulation, like the North Atlantic. It fundamentally sets the energy balance of the Earth. It sets, for example, where our tropical rainfall sits. If we slow the overturning circulation down in either hemisphere, we see a shift in the ITCZ, and that's because these overturning circulations set how much heat is transferred poleward. So it's a fundamental part of our climate system, just like the North Atlantic equivalent. Next slide, thanks, Neroli. Another perspective here is shown where we've sort of stretched out, or Mike Meredith in this lovely diagram stretches out the projection of Earth to highlight the fact that we do live on a planet with effectively one ocean. The basins that we talk about, obviously the Indian, the Pacific, and the Atlantic, are connected through the Southern Ocean, and it's Antarctica that sits at the center of the Southern Ocean. And this water mass that I'm describing today is so important for ventilating our ocean basins. Without the overturning circulations existing, we'd have a very stagnant, unhealthy deep ocean. That cycling of nutrients I mentioned would be limited to the upper ocean mixed layer, and that would have disastrous consequences for humanity. Next slide, thanks. This schematic on the right, well, it's actually not on the left, sorry, the schematic, it's not really a schematic except for the arrows. The red highlighted regions shows you exactly where this water mass is formed. It's formed on the shelves around Antarctica in 4 key locations. This red shading indicates just how strong that formation is, and it sinks to the ocean abyss, as I've mentioned. The green there indicates the age of the water, so the darker the green, the younger it is. It ventilates the world's oceans in this cascading flow off the Antarctic shelf. Next slide, thanks, Neroli. So I'm going to come back to these projections in a minute, but I want to make the point just quickly here that, as I've mentioned, we have 2 major overturning circulations in the world's oceans. The top panel here is this Antarctic overturning in a controlled climate simulation going forward in time in the grey curve, and then overlaid in this red curve is what we project will happen when we see climate change occur out over the next couple of decades. The diagram below, the blue curve, is the AMOC, the North Atlantic equivalent, and you can see that the slowdown that we simulate in this model projection is actually double the pace of the North Atlantic equivalent. So the Antarctic overturning circulation is far more vulnerable to climate change than the more famous North Atlantic equivalent. Both of these are critical overturning patterns for our world's climate system. Both are vulnerable to climate change, but the evidence we have over the last couple of years is that the Antarctic equivalent of the North Atlantic overturning is actually more vulnerable. If Neroli just goes back to the previous slide, part of the reason for this is these red patches of formation that I mentioned here in the left-hand panel. They are right at the front line of ice melt. Not just sea ice melt, but the land ice and the ice shelves right around Antarctica are contributing to a freshening of those water masses. Fresher water is more buoyant, it won't sink. and it sits at the surface rather than filling the ocean's abyss. If I was to show you the equivalent for the North Atlantic, Greenland is shedding meltwater, but the formation sites for the North Atlantic deep water are fortuitously a little bit further away from that ice melt region, and so the dilution from meltwater is just slightly less of a threat because of that distance the waters have to travel to effectively slow down the circulation. And if we now go back to the slide I was on, this is the reason why you're seeing this doubling of the slowdown of the Antarctic overturning. It's that situation of the water mass being formed right where the ice is melting at the moment. And we'll get back to that later in the talk when Neroli comes back to feedbacks between these different systems. Next slide, thanks, Neroli. So I'm just backtracking a little bit. We have had projections for some time now about this overturning circulation. Highlighted here in the diagram is what CMIP models were projecting at the last assessment report, about a 20% slowdown, 25% by the end of the century. Lots of variation across the models. But two big factors here. One is that the models are quite coarse resolution and don't capture those red formation sites I showed in the previous slide. And secondly, there's no meltwater included in these simulations. The coupled cryosphere bit of coupled models is only being added into those modeling systems at the moment. It's a very important thing that we're doing globally in the climate modeling community, is to bring coupled ice shelves and ice sheets into the prediction systems. But these last generation CMIP models did not include that meltwater effect. And if you click on one more slide, you can see the difference to the simulation that I just showed a couple of slides ago. This high resolution model we had published in Nature in 2023, this included those formation sites, importantly, right at the Antarctic shelf, but also we included projections of the meltwater trends playing out over the next couple of decades. And you can see it's a very dramatically more rapid overturning slowdown. We're getting to 40% slowdown by the middle of the century rather than 25% at the end of the century. Even more concerning when we go to the next slide is the early emerging evidence from observations, which is sparse and difficult to get to, and I'll get back to the observations in a minute. These observations are suggesting even that high resolution projection I show there in the magenta purple color, that even seems to be underestimating the pace of change, with changes at the moment of the order of 30% of a slowdown already by 2020, ahead of that 40% I mentioned by 2050. So this is not a good sign for this overturning circulation. And I just want to finish off by explaining how we can track this overturning. If we go to the next slide, Neroli. You can see here, this is the warming measured in the 2000s relative to the 1990s in the abyssal ocean below 4,000 meters depth. And you can see these red patches of higher than, the highest rates of warming are right around the Antarctic margin. Unfortunately, this is an indication of the slowdown. And the reason I say that is that we know this water mass is cold, fresh, and it's very dense. It's very oxygenated as well. So those four indicators tell us what that water mass signal looks like. And at the moment, we're seeing a warming of the water mass, and it's warming fastest right near the Antarctic margin. And we're also seeing a deflation of the oxygen. I didn't mention that in one of my earlier slides with the cross-section of the overturning. That was an oxygen color-coded in the background. This is like the lungs of the deep ocean. This is how oxygen gets into the abyssal ocean and is critical for the cycling of oxygen through the world's oceans. And we're seeing a deflation of those lungs. We're seeing the oxygen-rich layers slumping down decade by decade as this overturning slows down. If we go to the next slide, we'll see an animation of the simulation that I mentioned with the higher resolution and the meltwater, and you can see this fingerprint of an Antarctic overturning slowdown is so clearly emerging in this simulation. And as we run through to the 2050 point of the simulation, it should just stop there. This 40% decline has this exact footprint, and we can calibrate how the model is tracking compared to observations. And like I mentioned in the couple of slides ago, if anything, the evidence we have from this model simulation is that it's a little bit behind where the observations have got to. The pace of change is already at about a 30% decline. And this just tells you how critically urgent carbon emission reductions are, because we need to give this overturning circulation every chance of not tipping over what seems to be a very perilous and near tipping point. I think I'm handing back to Neroli now. Thank you.
Thanks very much, Matt. I'm now going to just touch briefly on the Antarctic ice sheet. And there we go. And so if I start by going back to this map of known tipping elements across the Earth system, you can see that there are known tipping elements when we start thinking about the Antarctic ice sheet, and particularly the West Antarctic ice sheet is an area that there has been substantial concern about for many decades because of the configuration of the way that the ice there sits on ground that is below sea level. As we're learning more about the ice sheet, we're also seeing that there are similar vulnerabilities in parts of East Antarctica as well. And our observations are starting to show substantial ice loss, both from the West Antarctic ice sheet, but also now starting to develop in some of those East Antarctic subglacial basins. The implications of losing that ice that is sat up on the Antarctic continent is that this is one of our major contributors to future sea level rise, and the commitments that we have for rising sea levels for coming decades to centuries and even millennia. One of the largest uncertainties when we look at this is the synthesis from the most recent IPCC assessment report, looking at what we could expect for future sea level rise based on different emission reduction scenarios. And even for the rest of this century, you can see that there are substantial uncertainties, particularly if we look at this dotted line. And this largely represents what might a low likelihood but high impact of future sea level rise look like if we were to more rapidly destabilize parts of the Antarctic ice sheet. And you can see those uncertainties then also widening when we go through to 2300. For the high emissions scenario, the scale is way off the scale represented by the slide here. But if we want to provide better information for countries and coastlines to be able to adapt to what the future looks like in terms of sea level rise, one of the things that we need to do is to have a better understanding as to where we're going to be losing ice from Antarctica and how quickly we might expect to lose that ice. So what we did in this paper was to have a think about how we can identify where we most need to put our attention for trying to understand the risk of future sea level rise coming from Antarctica. And so we can look at the way that the ice sheet is being observed to change. And this blue shading here is showing areas where we're observing changes. Things like the surface temperature is increasing, the elevation of the ice sheet is decreasing, the ice sheet is losing mass, and a few other parameters in there as well. And so that gives you this sort of heat map of where we're already seeing changes starting to develop in the ice sheet. And then we can also look at areas that we think could be particularly susceptible to rapid change. And this is thinking about where is the ice sheet sitting on ground that is below sea level, so a marine ice sheet. How much heat is being pushed into the ice sheet from below because of geothermal heat? What's the buttressing like of the ice sheet, largely from ice shelves that are floating in front of the ice sheet? And so thinking about those factors that could contribute to parts of the ice sheet being particularly susceptible to abrupt change. And if we combine that information, we get this map of vulnerability that really starts to pull out areas of concern. And these are areas where we can think about how do we best study those areas to have more certainty in what future sea level rise risk looks like. And an example of a campaign that we've run through the Australian Antarctic program over the last few years. This is a campaign focused on the Denman Glacier region. So I'll just go back. Denman Glacier is over in East Antarctica. It's one of the places that we're particularly worried about because the is in a very deep trough. possibly on ground that is up to 4 kilometres below sea level, so one of the deepest continental areas on Earth. And so through the Australian Antarctic program over the last number of years, we've run a campaign to study this area both from on the ground, looking at what can we measure about the ice sheet, the structure, what can we tell about the bedrock beneath the ice sheet, what's the ocean doing at the front of the ice shelf and at the grounding line, what does the climate variability in this area look like? And then last season, Australia's icebreaker Noina did its first dedicated marine voyage to the front of the Denman Glacier and did another whole host of measurements to try and put together the marine aspect, which, as Matt talked about, it's a really fundamental interaction in the Antarctic system, is this interaction between the ocean and the ice sheets. And so this is science that is now being developed and will be coming out over the coming years. Right, on that, I'm going to now pass to Jan.
Thanks, Nerali. Next slide, please. So the unique ecosystems of Antarctica and the Southern Ocean are also showing signs of abrupt change, and risks of abrupt change can be deduced both from observed biological regime shifts and also from our knowledge of adaptive capacity and thresholds of unique ecology of the Antarctic region. And habitat transformation leading to abrupt biological regime shifts has been documented both in Antarctic terrestrial and marine systems, with associated so-called winners and losers. In terrestrial biological systems of the Antarctic Peninsula region, warming has resulted in really rapid and self-perpetuating greening through colonisation of previously ice-covered or bare ground by mosses, as we see in the image here, algae and flowering plants, including some invasive species. And in other regions, Antarctic browning has been observed through declining health of moss beds due to extreme desiccation, which has been caused by reductions in the availability of moisture. And in East Antarctica, local habitat drying is leading to replacement of an Antarctic specialist moss with a cosmopolitan species. And this is actually an example of a potentially irreversible change to ecosystem structure in that region. Next slide, please, Nerali. Abrupt physical changes, including ice shelf collapse and sea ice loss, have also led to local regime shifts in benthic shallow marine communities. So these are marine communities that live on the sea floor. And what we see is that filter feeding communities that are shown on the left in the image here are being rapidly replaced by macroalgae dominated communities that is shown in the image on the right. And this response is due to increases in light, changes in sedimentation, and increased disturbance from iceberg scouring the bottom of the sea floor and have impact in that way. And these observed transformations in these benthic systems have frequently resulted in a reduction in biodiversity overall. Next slide, please. And contraction of the sea ice that we've heard about is also impacting other animals that depend on it for breeding and larval habitats, including krill. And krill are primary prey for many Antarctic megafauna, including whales, and also important mediators for biogeochemical cycling in the Southern Ocean, including processes that do enhance carbon sequestration. And there's evidence for a southward habitat contraction of krill populations in the southwest Atlantic sector, likely due to ocean warming and resulting changing sea ice dynamics, including the reduction of sea ice. And this contraction would increase interaction between the fishery and predators. And it's important to note that non-climatic stresses that may add to risk for rapid and widespread biological losses include other human pressures and disease. and this includes the current outbreak of avian influenza. Next slide, please, Nerily. On to Barbara.
Lovely. Thank you. Well, emperor penguins are an iconic species that is highly dependent on sea ice. And concerns about the future of these birds is forever increasing. Models have predicted a long-term population decline by the end of the century. Now, however, we have empirical evidence that the species is really facing serious threats. Next slide, please. The key, the key operating mechanisms include habitat transformation, for example, through the carving of icebergs, and increasing reproductive failures due to the untimely loss of their breeding habitat, which is the land-fast sea ice. Physiological thresholds may be crossed in future if the planet continues to warm, particularly when the environmental change occurs at a faster rate than the penguins can adapt. Next one. Most emperor penguin colonies occupy the land-fast sea ice, which is shown here in orange. Note that the fast ice is stationary, discontinuous, and varies in size in different areas. Also note that there are areas where no colonies appear. And to breed successfully, emperor penguins need fast ice that persists for at least 9 months a year. Next one, thank you. Iceberg carving is a natural event, and carving events significantly alter the ice scape. For example, 2 years ago, a giant iceberg called A81 broke off the Brunt ice shelf, and it took about 1,500 square kilometers of ice away. The yellow marker indicates where the Halley Bay colony used to be located, and if you look onto the right picture, you can see that the iceberg went and left the entire area as open water, which is not a good area for anybody to try and breed. Next one. Most penguins from the Halley Bay colony probably moved to the Dawson-Lambton colony about 60 kilometers south, but a proportion of unknown size moved eastwards, and this remnant of the Halley Bay colony is not out of the woods. They have found a bit of ice, but the ice quality is marginal at best. The images here are only a few weeks old. They're actually from this year, and you can see that already a substantial area of fast ice has been lost. And whether this continues, well, we'll just have to wait and see. Next slide. The early loss of fast ice can not only increase reproductive failure, it can actually cause the loss of an entire cohort of chicks. When a colony's breeding platform disintegrates before the plumage of the chicks is waterproof, the chicks will perish. The adults will survive, but the chicks won't. Here, in the next slide, you can see the same area and a massive amount of fast ice is gone. There were bits and pieces of fast ice left in the rifts of the Ross ice shelf, and it would not have been a complete breeding failure, but substantial numbers of chicks would have lost. You have to understand that they do not immediately die when the ice breaks out, but when they are set adrift on ice floes, there is simply no way that the parents coming back from a foraging trip will be able to find their chicks again. Okay, next one. The Antarctic environment is challenging and highly, highly dynamic. And no doubt disasters have befallen emperor penguins throughout their million-year-long history. And ice loss probably affected colonies here and there. But what happens, what appears to have changed in recent years, particularly since 2016, is that 34, that is just over half the colonies that we know of, collectively suffered no less than 78 early ice losses, and 21 colonies were affected more than once. These breakout events now occur every year and are also occurring right around the continent, which means there may not even be any safe areas for these penguins to go to anymore. And they occur even in areas that used to be known for the extensive and reliable fast ice cover. The top arrow actually shows you the history, the recent history at Halley Bay, and you can see that out of 8 out of 9 years, this colony failed completely in its breeding attempt. Calving events and early ice losses can be compounding. The Barrier Bay colony, which is indicated by the bottom red arrow, ceased to exist completely. We have not seen anybody there for the last 4 years because of both of those processes taking place. Next slide. The consequences of early ice loss are a threat to the long-term survival of the species. Important is that since they are long-lived, the impact of reduced recruitment will not become immediately apparent. Changes to colony populations also occur at different temporal and spatial scales, which makes it quite challenging to monitor. A great unknown is also how the food supply of the penguins may be affected. But even when we look only at alterations in the breeding habitat, the predicted probability that half the global population will be lost in less than 50 years is already 45%. In a warming world, it will be increasingly difficult for emperor penguins to find suitable breeding habitat. And these models do not even include any predictions about the loss of mold habitat during summer. As Ariane pointed out, loss of sea ice in summer is accelerating drastically. And that is a time when adult penguins molt and they need to be out of the water to survive the mold. So here is another threat that is of great concern. Thank you.
Thanks, everybody. And so I'm just going to do a quick wrap up, bringing all of those elements together. You've heard about the abrupt changes that we're seeing across the sea ice, in the ocean, on the ice sheet and ice shelves, and the impacts that has for the biological systems. And the speakers have also touched on some of the interactions that we're seeing between those different parts of the system. So when we think about abrupt change in the Antarctic environment, it's really important that we think about this in terms of the whole system and how these different elements interact and affect each other. So if we try and put together a schematic of this, there are multiple climate change pressures that are driving the abrupt changes that we're seeing across different parts of the Antarctic environment. This includes the climate warming, increasing ocean heat, sea level rise, changing weather patterns, and ocean acidification, and also not just the average changes that are resulting from climate change, but the way that these changes manifest in extreme events as well. And so there's these multiple pressures that are driving abrupt change. But there are also a number of amplifying feedbacks that we anticipate in the Antarctic environment. And so one of these Matt talked about, where if we slow down the overturning circulation and the formation of that dense shelf water right up around the coast of Antarctica, that allows us to bring more warm subsurface water up onto the shelf, which pushes in underneath the ice shelves and can cause greater melting of the ice shelf and ice loss. At the same time, as we're increasing the subsurface melting of ice shelves, we're putting more meltwater into the surface water, which is inhibiting that dense water production. So you can see this very close coupling and this positive feedback between these two abrupt changes in the Antarctic environment. And there are a number of other ways where we can anticipate that when we change one part of the Antarctic system, that has knock-on effects to increase the risk to other parts of the system. Barbara's just talked about the link between sea ice and fast ice decline and habitat loss and reproductive success for emperor penguins. That also has impacts on other Antarctic species. Again, when we lose Antarctic sea ice, we also expose the ice shelves around Antarctica to more physical damage from waves. So we have a number of these amplifying feedbacks between the changes that we're seeing in the Antarctic environment. But when we think about how these Antarctic changes feed back onto global climate change, we also see a number of amplifying feedbacks where the changes that are happening in Antarctica will have global impacts and worsen climate change. And Ariane talked about one of these in terms of what happens when we lose that reflective sea ice cover around Antarctica, the potential there for that to amplify regional climate warming. Matt also talked about the impact that changing the ocean circulation has on altering rainfall patterns. And there are, again, a number of these. So what can we do about this? If we think about the mechanisms that we have through international agreements to protect the Antarctic environment, these are coming through the Antarctic Treaty System. Many of these are really focused on how we protect the Antarctic environment, and particularly the biological environment. How do we reduce non-climatic pressures, and how do we establish protected areas? So those are really important interventions for strengthening the resilience of those parts of the Antarctic environment. But those interventions don't do anything to stop those multiple climate pressures that are having impacts across the Antarctic system. So if we want to actually address those multiple climate change pressures, that really leaves us with the only assured way of reducing the risk of further abrupt changes in the Antarctic environment is deep and rapid carbon dioxide emissions consistent with global agreements for emission reduction and the targets that we would want to keep global warming to within. But at the same time, we are already seeing at current levels of warming a number of these abrupt changes developing, and there are some changes that may be already unstoppable, particularly in terms of the way that Antarctica will contribute to future sea level rise, and potentially also that those long-term commitments for continued Antarctic sea ice decline. And so what that means is that as well as those actions to rapidly and deeply reduce carbon dioxide emissions, we also need to be thinking about how we set the world up to be able to adapt to plausible futures where we do have future abrupt changes coming from the Antarctic environment. So thank you very much for joining us today. We're happy to take questions from the floor. Again, highlighting that QR code there, that link will take you through to a website where you can access the scientific study and also the policy briefing materials. Thank you very much.
Thank you very much, everybody. Thank you for a really excellent talk. I don't know if you can hear the applause in the room, but yeah. So I'll open the floor to up to any questions on the floor. Yeah. Any questions? Great.
Hi, I'm going to ask you a really obvious question that I know you can't answer, but I want to hear what you want to say. What are the likely time scales for some of the abrupt changes to actually happen and then have the climate consequences? And I know we're hearing this week they're now saying, well, we're definitely looking at 2 degrees and we should do some preparation for 4 degrees. And you know, it's the big unanswerable question, but never mind.
I'm going to, I'll start with that, and then I'll see if any other of the speakers want to also address that. I would say that personally, I have been really surprised at how quickly these changes have already been developing around Antarctica. The changes that we've seen over the last decade, and particularly the last couple of years, have very much surprised me. So I think that we should be preparing for the possibility that there are further changes that we're not expecting from the Antarctic environment. But I think that the key message really is that even though we're talking about abrupt changes and things that don't scale with global warming, it again comes back to that message that absolutely every fraction of a degree matters in terms of the climate impacts and how challenging it is going to be to adapt to the changes that come from Antarctica that have global impacts. But also, if we want to be thinking about Antarctica as an area that we want to protect, and including the some of those iconic species like emperor penguins, which we don't find anywhere else on Earth, that really every decision that we make about reducing emissions matters in terms of potentially avoiding some of those worst case scenarios. Does anybody else want to add to that?
That's a great answer, Neril. I don't have much to add except to say that same point. You know, this is like a loaded gun, and we don't want to have too many bullets in the chamber. And every fraction of a degree loads us to more certainty about breaching these tipping points, because there do seem to be tipping points across the systems we've been talking about today. I was going to say quickly for the overturning circulation, what I presented, there is, you know, the Pritz Bay area is there are bits of those overturning circulations that might be more resilient. There are some that are right at the front line, like in the Ross Sea. So, you know, if we can stop global warming, the sooner we do, then there's a chance that some of the overturning hotspots can persist into the future. But it's definitely looking like, you know, the time for action is very much now. Thanks.
Thank you for that. Do we have any further questions? Yeah.
This is just a simple technical question. I really wanted to see the QR code, but if the technical person or someone could just move you people on the screen and put you to the side so we could see the QR code again, that would be really useful.
For those online, we have now moved the faces in the on Zoom.
Thank you.
Do we have any further questions on the floor? And if not, I have one quick question that I'd quite like to ask. You've talked a lot about the different tipping points, and especially Matt, you mentioned discrepancies between sort of models and observations and where we're looking at seeing these tipping points. Where do you see the priorities of observing these in the future? Where should we be looking? What should our priorities be?
I should let others speak to their different media, biological systems, sea ice and so on, but for the overturning circulation, it's certainly, you know, the Deep Argo program is very important for tracking changes around Antarctica. That's, for those of you who know about these Argo floats, they've been typically measuring only the top 2,000 meters of the ocean. Recently, they've been engineered to get to the bottom of the ocean. So those observations are critical for seeing this deflation of the overturning circulation. It is quite hard to get up onto the shelf where the formation actually occurs. It's formed during winter. There is generally ice getting in the way of making direct measurements on the shelf. So those Deep Argo floats are really critical for tracking that overturning. But I think the others may wish to comment on the other observing systems we need.
Well, I'll add to that because it's quite complementary. So in understanding the abrupt sea ice change, it's a really interesting scientific question because the sea ice sits at the interface between the atmosphere and the ocean. And what we think is happening over the past few years is really a result of subsurface ocean warming. But like Matt's talking about, we lack observations of what the ocean is doing under the sea ice. So in addition to these deep Argos that can observe the deep ocean, we really need to get more ocean observations underneath the sea ice so that we can better understand what's the ocean doing, how might it be getting heat up to the sea ice that is preventing sea ice growth and melting back sea ice.
Jan and Bob, did you want to add anything on biological systems?
Well, the trouble is that while they are quite complicated and far-reaching models already with regard to predicting or analyzing the population trend of emperor penguins, as I mentioned before, you know, there are simply a lot of variables that are not captured yet, and they are so important. The trouble also is that with regard to the megafauna, the changes can actually be, the environmental changes can be quite localized. They may not even be on anybody's radar. And that makes for a huge amount of variability in the environment, which will be very, very difficult to model. And I guess the only thing we can do is continue our observations and continue to monitor and add more data to what is hopefully going to become a model at some point that can be a little bit more reliable.
I will add, in terms of Antarctic research, I think one of the challenges that we've always faced in trying to observe Antarctic changes and understand them is how difficult it is to collect information from Antarctica. But I think that we are seeing a whole range of technology advances that are really game-changing in terms of what we can do in terms of being able to study Antarctica, particularly some of those technologies that don't require getting people onto the ground. We've got autonomous vehicles and drones and other ways of remote monitoring that are really opening up a lot more information for being able to detect changes in the Antarctic environment. And then the other really important aspect for the work that happens in Antarctica is the international collaboration. So Antarctica is this area that's reserved for peace and science, and the international collaboration there is a really important aspect of that. And so in the coming years, there's a program called Antarctica in Sync, where nations who work in Antarctica are coming together to look at how we can design scientific programs together to make the most of the observations that we're collecting in Antarctica. And that proceeds then moving into the International Polar Year, which again will be another great catalyst for really looking at how we can work together as an international community to understand the changes that are happening in Antarctica and to provide improved information to decision makers.
Thank you very much. I think we have time for one more question. Looking around, and if not, we'll say thank you once again to the Australian Antarctic Division and for an excellent talk. Thank you.
Thanks very much for joining us today.
Well done, team.